Welcome to Part 5 of this week's online lecture. In Part 5 we will discuss Cartesian displacement coordinates. It isn't always easy to select suitable internal coordinates to describe the vibrations. In particular, the chosen coordinates should be independent, and frequently this is not obvious. We need a more general approach. One such approach is to define Cartesian displacement coordinates for each atom. To illustrate, we can repeat the analysis of ammonia using such a coordinate system. For ammonia, the symmetry of the molecule tells us to treat the three hydrogen atoms together, as the symmetry operations will exchange the coordinates on these atoms. The central nitrogen atom is treated separately from the hydrogen atoms, as there is no exchange of coordinates between those associated with nitrogen and hydrogen atoms. Treating the atoms separately reduces the complexity of the problem, but is not essential. That is, we could treat all the atoms together. In total, there are 9 Cartesian coordinates on the hydrogen atoms and 3 Cartesian coordinates on the nitrogen atom. However, group theory allows us to separate the symmetry of an arbitrary x, y and z set of coordinates from the symmetry of the atoms themselves. So the first thing we need to do is identify the representation associated with the x, y and z coordinates, and we can do that by simply inspecting the character table. In the C3 point group, z transforms like A1, and x and y transform like the degenerate irreducible representation E. To find the representation of x, y and z, we simply write down the sum of the A1 and E representations. For the identity, the character is 1 plus 2 is equal to 3. For the C3 class, the character is 1 plus minus 1 is equal to 0. And for the sigma V class, the character is 1 plus 0 is equal to 1. Note that the sum is three-dimensional. The character under the identity is 3. One dimension for each Cartesian coordinate. Next we need to find the character for each set of atoms. This is determined by adding 1 for each atom that remains in its original position and 0 for each that changes position. The table gives the representation for the nitrogen atom, which is left unchanged by each symmetry operation as it is at the centre of symmetry of the point group. Therefore its character under each symmetry operation is 1, and the resultant representation is the totally symmetric representation A1. The table also gives the representation for the 3 hydrogen atoms. In this case, the character under the identity is of course 3, as all 3 atoms are left unchanged. And under the sigma V class, 1 atom is unchanged and the other 2 move, and so the character is 1. Note that for the C3 and sigma V classes, you only consider one member of the class. We can now determine the representation of the x, y and z coordinates on each set of atoms. It is simply the product of the representation of x, y and z with the representation of each set of atoms. So in the table, the first 3 rows give the representation of the x, y and z coordinates, the representation of the nitrogen atom, and the representation of the 3 hydrogen atoms. However, we want to know the representation of the x, y and z coordinates on the nitrogen atom and the x, y and z coordinates on the 3 hydrogen atoms. To find this, we simply take the product as illustrated. For nitrogen, the product of the x, y and z representation with the nitrogen atom representation is 3 times 1 is equal to 3 under the identity, 0 times 1 is equal to 0 under the C3 class, and 1 times 1 is equal to 1 under the sigma V class. For the hydrogen atoms, the product of the x, y, z representation with the 3 hydrogen atoms representation is 3 times 3 is equal to 9 under the identity, 0 times 0 is equal to 0 under the C3 class, and 1 times 1 is equal to 1 under the sigma V class. These representations can then be reduced as indicated in the right-hand column of the previous table. Thus the motions of all the nuclei span 3a1 plus a2 plus 4e. This is simply found by adding together the representations for the displacement coordinates for each of the hydrogen atoms and nitrogen atom. Note that choosing 12 displacement coordinates for a tetraatomic nonlinear molecule means that we will be identifying the symmetries due to all degrees of freedom, that is, due to translations, rotations, and vibrations. We are only interested in the vibrational symmetries. So in order to identify the vibrational degrees of symmetry, we need to remove the translational and rotational symmetries. However, the translations of the molecule as a whole transform, not surprisingly, as x, y, and z, that is, A1 plus E, and the rotations are given in the character table and transform like Rx, Ry, and Rz, that is, A2 plus E. So we must subtract these to leave the symmetries of the true vibrations. So if we started off with 3a1 plus a2 plus 4e for the 12 displacement coordinates, and we take away a1 plus e for the translations and a2 plus e for the rotations, we are left with 2a1 and 2e as the symmetries of the true vibrations. Let's consider another molecule, this time methane. Methane has TD symmetry. The point group has 5 classes of symmetry operators: the identity, the C3 rotations, the C2 rotations, the S4 improper rotations, and the mirror planes. There are 2 C3 axes about each CH bond, and so there are 8 in total. There are 3 C2 axes, which can be identified with the X, Y, and Z axes passing perpendicular through the faces of the cube in the figure. The S4 axes are aligned with the C2 axes. The mirror planes contain a set of HCH atoms. There are 6 possible combinations, and so 6 mirror planes. The symmetry of the molecule means that we can separate the Cartesian displacement coordinates on the carbon atom from those on the hydrogen atoms, and we can apply the same methodology as we did with ammonia. In the TD point group, X, Y, and Z transform like the three-dimensional irreducible representation T2. The representation of the central carbon atom will be the totally symmetric representation, which is the A1 representation, because the carbon atom remains in its original position during each symmetry operation of the point group. Therefore, the representation of the X, Y, and Z coordinates on the carbon atom is simply T2. For the 4 hydrogen atoms, the character under the identity will be 4, the character under C3 class will be 1, the character under C2 class will be 0, the character under the S4 class will be 0, and the character under the sigma D class will be 2. Therefore, the representation of the X, Y, Z coordinates on the 4 hydrogen atoms will be 3 times 4 equals 12 under the identity, 0 times 1 equals 0 under the C3 class, minus 1 times 0 equals 0 under the C2 class, minus 1 times 0 is equal to 0 under the S4 class, and 1 times 2 is equal to 2 under the sigma D class. We can then reduce this representation to find that it spans A1 plus E plus T1 plus 2 T2. Let's make sure that the dimensionality has not changed. A1 is singly degenerate, E is doubly degenerate, T1 triply degenerate, and T2 is triply degenerate. The overall dimension is 1 plus 2 plus 3 plus 2 times 3 is equal to 12, the same number of coordinates as in the basis set. Note further that you can check to make sure that these irreducible representations are the decomposition by simply adding up the irreducible representations A1 plus E plus T1 plus 2T2. Doing this gives you 12,0,0,0,2 for the representation. Under this point group, translations transform like T2 and rotations transform like T1. so the pure vibrations transform like A1 plus E plus 2T2. If we wanted to know which of these vibrations are stretching vibrations and which are bending vibrations, then we could use displacement coordinates along the bonds to determine the stretching vibrations. We would find that the stretching vibrations span A1 and T2. This means that the remaining vibrations must be bending vibrations. This means that the bending vibrations span E and T2. It should be noted that it is frequently more important to identify the symmetries of the stretching vibrations than the bending vibrations, because in general they involve force constants that are much larger and therefore appear in the infrared spectrum at higher frequencies, that is, outside of the fingerprint region. Also, assuming that the vibration is infrared active, stretching vibrations are also in general more intense than bending vibrations, as they normally involve bigger changes in the dipole moment during the vibration. This is the end of part 5 of this week's online lecture. Please continue on to part 6.